So I had this really weird experience the other day. I asked an AI for, a simple recommendation, and it gave me something just so bizarrely confident but completely wrong. It really made me question things.
Oh, really? What kind of blunder was it? Sounds intriguing.
Well, let's just say it involved pizza toppings falling off
Yeah.
and a very unconventional suggestion involving glue.
Ah, yeah.
Yeah. It got me thinking, like, how often do these AIs just confidently tell us total nonsense?
That's actually a perfect example of what people in the field call an AI hallucination.
Hmm.
It's different from human mistakes, right?
Yeah.
We might misunderstand or misspeak, but AI can just generate completely fabricated information. And the really tricky part is it presents it with such, stunning confidence.
Right. And then if you ask it to try again, it might say sorry, but then it just makes up something else entirely different. It makes it hard to know what parts you can actually trust.
Exactly. It's frustrating.
Totally. And if we're going to start relying on AI for, important decisions, hopefully things more critical than pizza repairs, then we really need it to be accurate. So that brings us to the big question. What can we actually do to make AI more accurate?
Well, that's pretty much the mission for our deep dive today. We've looked at a bunch of sources, research papers, articles, and they explain some of the main techniques people are using right now to improve AI reliability. So hopefully you can avoid those pizza and glue situations yourself.
Okay, great. Let's get into it. So the core problem we're talking about here is these AI hallucinations. An AI model, particularly these large language models, the LLMs, they're trained on a huge but specific set of data, right?
Right. It basically knows what it knows from that training data. That's its world.
But what happens when someone asks a question and the answer needs information that just wasn't in that training set? Maybe it's like super recent news or just something niche that wasn't included.
Yeah, and this is where it gets, well, interesting and sometimes problematic. The LLM will still try to give you an answer. It typically doesn't just say, sorry, I don't know that.
Mm.
Instead, it'll generate a response that sounds plausible, sounds confident, but it might be completely made up, a hallucination.
Like the industrial glue for my pepperoni problem.
Exactly like that. Plausible structure, terrible content.
So to stop getting these, confidently wrong answers, we need ways to either feed the AI trusted information when it needs it or sort of guide its thinking process more carefully.
Precisely. And that takes us right into the first major technique people are using, something called RAG.
RAG. Okay, and that stands for retrieval augmented generation, right? Not like actual RAG.
Haha, no fabric scraps involved. Retrieval augmented generation. It's a clever way to tackle this.
So how does RAG actually work? How does it make the LLM give better answers?
Well, the key idea behind RAG is injecting relevant, trusted information right when the LLM needs it for a specific query. It's about making the model more current and reliable without constant massive retraining. So before the main LLM even gets your question, there's another component, a retriever. This retriever goes out and searches a specific, trusted data source.
Like a curated database or a set of company documents?
Exactly. Often it's something called a vector database, which is really good at finding information based on meaning and relevance, not just keywords. Think of it like a really smart librarian. This retriever finds and pulls back documents or pieces of text that are highly relevant to your specific question.
Okay, so it finds the potential facts first from a place we trust.
Yes. Then, this extra information, this trusted context, gets added to your original prompt. It sort of embellishes or augments what you asked. This augmented prompt then goes into the LLM's context window. That's like the AI's short-term memory for the current task.
Ah, I see. So it now has a specific info it was missing before.
Right. And with this richer fact-checked context, the LLM can then generate its answer. That's the G in RA. The hope, and usually the result, is a much more accurate, grounded response because it's not just guessing based on its original training data anymore.
That makes a lot of sense. Grounding it in facts just in time. Okay, so RAG helps fix the knowledge gap. But what about the model itself? If the AI's base knowledge isn't perfect, maybe the type of AI model we choose matters too. Which brings us to technique number 2, picking the right model.
Absolutely. It really is like picking the right tool for the job. You need a model that's, well, fit for the purpose you have in mind, things like the model's size, how big it is, and crucially, the specific data it was trained on. These massively impact its accuracy for different tasks.
Okay, so how does that play out? Like big model versus small model?
Well, think about it this way. A really large general-purpose model, one trained on tons of different topics, medicine, law, coding, art, history, you name it. That kind of model is probably less likely to hallucinate if your question is pretty broad or if it touches on several different areas. It has a wide, if not always super deep, knowledge base.
Okay, like a generalist.
Exactly. But then you have smaller models.
Yeah.
These might be trained with much more specific information. Let's say one is focused only on cybersecurity knowledge. Now, that model is much less likely to hallucinate if your question is squarely within cybersecurity. It's an expert in its narrow field.
Right, okay. It reminds me of the analogy you sometimes hear. You wouldn't ask your family doctor for detailed advice on fixing a computer virus, right? But you would ask them about a biological virus.
Perfect analogy. The medical doctor excels in their domain. The general model is better for broad questions. Ask that general model a really deep, specific cybersecurity question, and you might get a shaky answer, maybe even a hallucination. But ask this specialized cybersecurity model that same question, and you'll likely get a much more accurate, detailed response.
But the flip side is true too, isn't it? If I ask the cybersecurity expert model about, I don't know, Renaissance art, it might completely bomb or just make something up.
Precisely. It's outside its expertise. So the key takeaway is you really need to match the model to the domain of your questions. Optimize for the task.
Makes sense. Okay, technique 3 sounds interesting. Chain of thought prompting, COT.
Yes, chain of thought. This one's about how you ask the question, or rather, how you guide the AI to think about the answer. The basic idea is to get the LLM to explicitly write out its reasoning steps, its intermediate thinking, before it gives you the final answer.
Like showing your work in math class.
Exactly like showing your work. And just like in math class, it really helps reduce mistakes, especially for problems that need logical steps or calculations. It forces a kind of logical consistency.
I definitely remember my math teacher insisting on that. Okay, let's use that math example from the outline, the widget factory one. So the factory makes 3 times as many red widgets as blue ones. Total production is 240 widgets. How many are blue?
Right. And if you just take an intuitive guess, like the LLM might, you could easily land on something like 80, maybe dividing 240 by 3.
Yeah, my first thought might be 80. But that's wrong, isn't it?
It is. But if you show your work, let's say B is the number of blue widgets.
Okay, so red widgets would be 3 times B, so 3B.
Right. And the total is blue plus red, so B plus 3B must equal 240.
Which means 4B equals 240, so divide 240 by 4.
And you get B equals 60. 60 blue widgets, see? Going step by step gets you the right answer, avoiding the intuitive leap.
That's a great illustration. LLMs can make similar intuitive leaps that are wrong. So how do we actually get the LLM to do this show your work thing?
There are a couple of main ways. The simplest is called zero-shot COT. You basically just add a little phrase to your prompt, something simple like, let's think step by step. Just adding that trigger phrase can often nudge the model into generating that reasoning chain first.
Just like that.
Yeah.
That's surprisingly simple.
It often works. Another way is few-shot COT. Here you give the model examples in the prompt, so you might include a couple of math problems with their step-by-step solutions already worked out. The model then sees the pattern, sees how you want it to reason, and applies it to your actual question.
Learning by example.
Exactly. And nowadays, some of the newer models, especially those built specifically for reasoning tasks, kind of have this chain of thought process built in more deeply. They're designed to think that way more naturally.
Okay, so chain of thought seems really powerful for logic, math, reasoning. But what about just knowing facts? If the problem isn't about deduction, but just retrieving knowledge, does COT help there?
That's a really important point. Chain of thought is fantastic for improving the reasoning process.
Yeah.
But if the core issue is that the model just doesn't know a piece of information, COT doesn't magically fix that. It mainly helps with problems where the answer can be derived logically from the information given, not so much for pure knowledge recall.
Got it. Different tool for a different type of accuracy problem. Okay, let's move on. Technique 4. LLM chaining. This sounds like getting multiple opinions.
Yeah, you can think of it that way.
Yeah.
It's about leveraging more than just one AI brain to try and arrive at a better, more reliable answer, getting a sort of consensus.
How does that work in practice? Do you just ask 3 different AIs the same question?
Well, there are different ways to set it up. One common pattern is kind of like a revise and reflect process.
Yeah.
Imagine you have, say, 3 different LLMs. You send the prompt to the first one, it processes it, maybe generates an initial response or some thoughts, and then reflects on it, passing its output to the second LLM. That second LLM then takes the input, maybe revises it based on its own training and perspective, reflects, and passes it on to the third. It's this sequential process, building on each other's work, leveraging the sort of collective intelligence.
Interesting. So it's like an internal peer review process, refining the answer as it goes along.
Exactly. It
Yeah.
taps into the idea that different models might have different strengths or catch different errors.
Mm.
Another variation, which is also quite common, involves having a kind of supervisor or decider model,
A boss AI.
sort of. In this setup, the supervisor model gets the initial prompt. It then sends that prompt out to several other LLMs simultaneously, let's say R3 again. Each of those worker LLMs comes up with its own answer independently. They send their answers back to the supervisor.
And the supervisor picks the best one.
Or even better, it critiques all the responses. It analyzes them, maybe combines the best parts of each, or identifies inconsistencies, and then generates the final consolidated answer. It's like the AI being its own critic, or using that wisdom of the crowd idea, like phone a friend, but the AI does the calling and synthesizes the advice.
That sounds incredibly sophisticated, a way for the AI system to self-correct using multiple perspectives. Are there other ways to get this kind of multiple opinions benefit?
Yes, definitely. Which brings us neatly to technique number 5, MOE. It stands for Mixture of Experts.
Mixture of experts. Okay. Sounds similar to chaining, maybe. Getting different experts involved.
Similar principle, yes, leveraging multiple sources of intelligence, but there's a really key difference in how it's structured.
Okay, what's the distinction?
With LLM chaining, we were talking about using multiple, separate, independent LLM models working together. With Mixture of Experts, or MOE, we're actually talking about components within a single, very large LLM. So imagine one giant model, but inside it there are numerous smaller, specialized submodels. Each one is an expert in a particular domain.
Ah, okay. So within the one big model, you might have an expert submodel for math, another for legal stuff, one for creative writing, one for coding, things like that.
Exactly, all housed within the same overall architecture. And here's the clever part. There's usually a component called a gating network,
A gating network, like a router.
precisely like a router. When your prompt comes in, this gating network analyzes it and decides which expert, or maybe which combination of experts, is best suited to handle that specific query. It then routes your request only to those relevant expert submodels.
So not all the experts are activated for every single query.
No, that's the efficiency gain. Only the relevant ones fire up. Then, the outputs from those selected experts are combined to produce the final answer.
That sounds really efficient. You get the breadth of a huge model, but the precision of specialists, and potentially faster responses because you're not running the whole massive thing every time.
That's the idea. It allows the model to handle a much wider range of complex patterns because it can delegate tasks to the right internal specialist. That's like, as you said, using one brain, but routing the question to the specific lobe best equipped to handle it reduces errors through that internal specialization.
Fascinating. Okay, another parameter we hear about sometimes is the temperature setting. What's that about? Does it make the AI more chill?
Yeah, not quite about its mood. The temperature setting is a parameter you can often adjust that controls the randomness, or maybe think of it as the creativity versus the predictability of the AI's output.
Okay, creativity versus predictability. How does that work?
So a very low temperature, like close to 0, say 0.0 or zero point 0.1, that makes the output much more deterministic. The AI will tend to pick the most statistically likely next word or token. This leads to answers that are very focused, factual, consistent, and predictable. Less variation each time you ask.
So if I need reliable, straight facts, like for a science question or summarizing technical data, I'd want a low temperature.
Exactly. Low temperature is good for reliability and consistency. Now, if you crank the temperature up, say, towards 1.0 or even higher, the AI is allowed to consider less probable words more often. This introduces more randomness, more variety. The output becomes more creative, less predictable, potentially more novel or unexpected.
Ah, so that's where you'd use it for things like brainstorming ideas, writing poetry, or maybe drafting different marketing slogans, where you want variety and maybe some surprising connections.
Precisely. High temperature is for creative tasks, where you value originality over strict factual repetition. The crucial thing here is that there's no single right temperature. It totally depends on your use case. What are you trying to achieve with that particular prompt?
Got it. Adjust the dial based on the job. Okay, we've covered a lot of ground. Any other quick techniques we should mention?
Yeah, a couple of important ones. First, the system prompt. This isn't something you type in every time, usually. It's more like a background instruction, often set by the developers or maybe configurable by the user, that tells the model how to behave generally. It's like setting the AI's personality or core directives.
So it might be told you are a helpful assistant or answer concisely or maybe even never provide medical advice.
Exactly. It's a foundational instruction. And you can definitely use system prompts to encourage accuracy, maybe by telling it to always state sources or admit when you don't know. It can also set guardrails against misuse, like prompt injection attacks.
Okay, that makes sense. A baseline instruction. And the last one.
Reinforcement learning with human feedback, or RLHF. This one's huge and has been key to making models like ChatGPT much more helpful and safer.
RLHF, how does that work? It sounds like humans are directly involved.
They are. It's basically a training loop where humans provide direct feedback on the AI's responses. After an AI generates an answer, human reviewers might rate it, maybe give it a thumbs up or thumbs down, or even rewrite it to be better. This feedback is then used to reinforce the model's behavior, rewarding good responses and disincentivizing bad ones. It's a way to fine-tune the AI based on human judgment of what constitutes a high-quality, accurate, and helpful answer. It's like constantly teaching the AI based on real examples.
Wow, okay, so humans are actively helping to shape the AI's accuracy and alignment.
Very much so. It's a critical part of the development process for many state-of-the-art models.
So we've covered RA, picking the right model, chain of thought, LLM chaining, mixture of experts, temperature, system prompts, and RLHF. That's quite a toolkit.
It is, and these are definitely some of the primary ways people are working to make AI more accurate and reliable right now.
Right.
But, and this is important, none of these are a silver bullet, right? None of them are perfect on their own.
Right.
Often, building a truly reliable AI system involves using a combination of these techniques, thoughtfully applied depending on the specific challenge. It's
Correct.
still a really complex and fast-moving area.
Absolutely. It feels like we're constantly finding new ways to nudge these incredibly powerful tools towards being more consistently truthful and useful. So, thinking about all these methods we've discussed, what are your thoughts? Are there other techniques you've encountered or think are promising for ensuring AI accuracy? It's definitely something worth pondering as we all navigate this evolving landscape.